Okay, hi everybody. We're going to be doing a little work on vectors, and I'm assuming that last term, when you did Physics 11, that you've already had some experience using these things. But in Physics 12, we're looking more at seeing vectors being used in two dimensions. Now, you probably did mostly one-dimensional work before. You probably did a little bit, but what I want to do is I want to go through a single question and just go through all the steps and then give you a worksheet that you can do a little more practice on. So I want to make sure that you just pay attention to all the steps that I go through in solving this problem, so that maybe some of the gaps in what you know is cleared up. So let's go through this problem. I've got a set of forces that are applied to a 10 kilogram mass as shown. So what we're looking at here is a free body diagram where you always show in the center the mass you're talking about, and we just show a point. And then we always show, starting from the tip to the tail, all the forces going out from that center. That's how we draw a free body diagram. We never draw it with the arrow going in. It's always drawn outwards. And then we label them all. So we see we have a 2 Newton, a 4 Newton, a 4 Newton here, and a 5 Newton. So we got a bunch of them. And we want to know, what is the resulting acceleration on the mass? So I know that force net is equal to mass times acceleration. And these are vectors. I have to remember that's a vector. I know the mass. So I know that it will be a 10 kilogram mass times my acceleration, but I don't know what the acceleration is. And I don't know what the net force is. So what I have to do is I have to find the net force. So that means, now notice, it's a vector. So I need to know the magnitude, and the direction. I need to know both of that. So I need to know what the net force vector is. And the only way to do that is I need to add up all the vectors. But x and y components, I have to add those up separately. I do that first. I can combine it later, but first I have to looking at all of them separately. So I want to sort of see what is the x's and what is the y's. And when I say x and y, I'm sort of deciding, in this case, x is right and left, and y is up and down. So I got to look at this. So let me see. So let's look at f net x, the x components. So what do I got? I've got a 4 Newton and I've got a 5 Newton. But the 5 Newton is going to the left and the 4 Newton is going to the right. So right away I have to decide which direction is positive. So I'm going to, let me see over here. I'm going to add this. I'm going to assume to the right and also upwards. Upwards is positive. And it doesn't matter. I could have chosen the other way. I could have chosen that left was positive. It doesn't matter. The only thing that's important is that I do the same thing all the way through. So I've just decided, okay, this way to the right, that's positive, to up is positive, and that way is negative, and down is negative. Okay. All right. So let's quickly erase that. All right. So now what? Well, let's look at the x components. Now I've got a positive 4 Newton. I've got a negative 5. Now here's the problem. I've got a forenewton that's actually at an angle. So let's look at that. The forenewton is at an angle, so it's not pointing directly right, left, or up and down. It's actually made up of two parts. So I'm sure some of you guys already know what you have to do here. But what we're looking at is saying, well, wait a minute, the forenewton is kind of made up of a x component and a y component itself. So how do I find it? Well, I know that this is let's look at it as a triangle. I've got, here's my x, here's my y, and here's the 4, because the forenewton is what looks to be, well, wait a minute, it's a right triangle, so this is a hypotenuse. And I also know, well, this is, if this is 30 degrees, then this right here is 60, and, well, this is 30 degrees too. So I have a nice little parts here. So if I wanted to look at, say, the x component, how do I do that? Well, this is where a little bit of trigonometry comes in. So I do know, let's say if I had 60 degrees, cosine, let me see, what would I say? Cosine of 60 is equal to, well, that's, what is that? That's, well, that's adjacent. It's adjacent over my hypotenuse. That's, oops, spelt it wrong. Don't want to spell it wrong. Adjacent over hypotenuse. And so in this case, that would be equal to my x all over my 4. So if I had to solve for this, I could say that, well, if I just play around a bit, I would find that x, my x component is equal to 4 times cosine 60. Now, if I take out my calculator and I find out what cosine 60 is, you'd very quickly find that cosine 60 is 0.5. So it's 4 times 0.5. Half of 4. So 2 newtons. So this here is equal to 2 newtons down. Now what about my y? My y, and notice, I got to make sure I'm pointing it in the right direction. So this is actually negative 2 newtons because I'm pointing down. And y is going to be going to the left, so it's going to be negative as well. But what is it? Well, the y. How do I find the y? Let's do it over here. Well, I could do a cosine again from here. I could say that, let me see, cosine 30 is equal to y over 4. Right? The adjacent over hypotenuse. So therefore, y equals 4 times cosine 30 degrees. So what's 30 degrees cosine? Let's plug her in. We get something a little more fancy. That'll be 4 times, now I'm just rounding up a little bit. I got 0.866. And that's equal to, let me see, 4 times, that gives me 3.464, let's say for now, newtons. So this up here is equal to negative, remember it's going to the left, it's negative 3.464. So now I've got all my parts, all the different forces in either the x and y direction. So I don't have to look at the 4 anymore, I have to look at the negative 2 and the negative 3.464. So now when I look at my x, my net x force, I have to include this y component here. So I'm going to say, let's see, minus 3.464. So what do we got? That'll be, let's see, well, let's just add it up. That's that, minus 5 plus 4. What do I got? I've got minus 4.464 newtons. Okay. So let's see, what's the next thing I gotta do? I gotta get the net y's. Now what do we got? Well, I basically only have the negative 2 and the 2. Oh, well, this is going to be pretty easy because I get a 2 newtons minus a 2 newtons. And what do I got? 0. I got 0. I actually have no y component in this case, which is pretty awesome because that means all I have. So therefore, this is, by the way, this is a symbol for saying, therefore, dot, dot, dot. F net, my total F net, is equal to negative 4.464 newtons to the left. That's basically what I'm doing. I'm going straight to the left. Now, if that's my net force, what do I got to do now? Well, not too much there. Basically, I'm saying that negative 4.64 is equal to 10 kilograms times my acceleration. So my acceleration is nothing more than that divided by 4. So it's 0.4464. And actually here, I better give a little room here just so I can include my meters per second squared. Now, am I totally done? Well, not entirely. What I have to be careful about here is my significant digits. We can't forget that. Now, interesting thing is that the way I wrote this is I wrote it where I only have one significant digit when I talk. So technically, I can only say one significant digit here. So it's 0.4 meters per second squared. That's actually my answer. Because notice there's one sig digit. And the rules is that I have to use the value that has the smallest significant digit. So I don't really have much of a choice there. Now that worked out really well for me. I could have had a situation where my net forces, let me see. I could have had a situation where my net force wasn't all in one direction. Now Now you might have said, well, what if your x components and my y components? I had amounts for both. So what if I had F net? Now I'm just pretending here, but F net x turned out to be 4 newtons to the right, and my y. What if I had a y value? F net y turned out to be equal to 2 newtons down. So negative 2 newtons. What would happen there? Well, it's very similar to what you would have done here, because you could have, all you would have to do is draw it. So you would have said, okay, here's my point. I've got 4 newtons that way. Remember, I'm just making these up. This is just to show you what you would have to do. And then you would have 2 newtons down. So my final, let me see, I'm going to get another color here. My total, my actual F net, whoops, get all that different color if I'm not going to use it. Here we go. Whoop, there, nice. So this is my actual net force. It's combining these two. So how do I do it? Well, this is nothing more, let me see, there we go, nothing more than Pythagorean theorem again. I'm doing a right triangle. So how do I get net force? F net would then be equal to, and now this is the magnitude, I don't know the direction yet, is equal to, now I'm just simply using c squared equals a squared plus b squared, right? That's all I'm doing. So the net force would be the square root of 4 squared plus negative 2 brackets squared. So that would be the square root of 16 plus 4, which is nothing more than the square root of 20. What is that? 20 would be square rooted into roughly 4.47 newtons. Now the question is, well, that's great, Mr. Gale, but what about the angle? I mean, there's obviously an angle here. Some angle, we'll call it theta, right? What is that? What is that angle? Well, let's just do it real fast. I know all sorts of things here. So I could say, well, why not just do this? The cosine of the angle is equal to the adjacent 4 over the hypotenuse, which now I know, 4.47. And therefore, let me see, the angle is equal to the inverse cos of 4 over 4.47.